In this lesson, we're going to be learning how to solve exponential and logarithmic equations and then applying those equations in real-world situations. Today, we're only going to learn how to mathematically solve them. Next class, we will do all of the real-world scenarios, which are actually very cool. So first things first, solving exponential equations. There's a few steps to being able to do this, and it does utilize the idea of logarithms and exponentials being inverses of each other. First thing we're always going to do is work to isolate the exponential expression, which is the b to the x. So base with the power needs to be its only thing on its side equal to some number for us to be able to do this. Then we're going to take the natural log of both sides. So we will literally put ln, natural log, on both sides. So we are taking the natural log of both sides. And then apply either the power rule or the identity. Now the power rule, remember, is that if you have an exponent, let me actually highlight that, an exponent there, we're going to be able to move it to the front of the logarithm so that it's here in front. Or the identity, which is when the bases match, that we get to cancel them out. So logarithm base b of b to the x, since the bases are the same and you have an exponential tucked inside a logarithm, they will cancel each other out. And then we'll just solve for x like normal. So obviously I've done a few of the examples for you, and we will go through them, and some of them we will do together. First things first, we want to make sure that the base with the exponent or the exponential expression is isolated. Cool, done, awesome, we got it. The next thing we're going to do is take the natural log of both sides. So like literally write natural log of whatever is on the left-hand side and natural log of whatever is on the right-hand side. For this one, since the bases do not match here with natural log of 6, we're going to use the power rule, which means we can take this exponent x and move it to the front. So that is going to be x times the natural log of 6 equal to the natural log of 42. My last step is to solve for x. Well, if I want x to be by itself, I would need to divide both sides by natural log of 6. I'm going to do that. And natural log of 42 divided by natural log of 6 is not something I can do in my head, so I asked my calculator to compute that for me, and I would round to the nearest thousandth, which is 3 decimals, and get 2.086. Now, here's something really interesting that I want you to be able to do. When you have this as your answer, like literally the last thing you've typed in your calculator is natural log of 42 divided by natural log of 6, you are going to check your work by doing the following. In your calculator, you will type 6 and then answer. Now, the answer key, if you're looking at your calculator, so go ahead and look at it, is a blue word over the negative sign, ANS. So I would press second negative, and what it's going to do is it's going to plug in your answer, which is this entire thing, not rounded, but the entire x value, into x. So we're going to raise 6 to that entire decimal, not the rounded version we wrote on our paper because we just rounded it. And if we press enter and get 42, then we did it right. And when we do get 42. So we're able to check our work. Again, we're using this answer key to check our work each time, which is above the negative. It's a blue. So second negative would plug in the previous answer into whatever you're typing. If you need me to explain this to you, probably want to ask about that just right now because I'm expecting that you know how to check your work. Okay. Now this next example, obviously I've done it for you, but on your copy there's not all of the annotations that I have. So let's look at those annotations. Now I'm not going to write anything down, but I would recommend you annotating this problem as we go. From the first step to the second step, obviously since we needed to isolate the term with an exponent, I added 3 to both sides so that this was the only term there. Then I took the natural log of both sides, which allowed me to use that power property to take this exponent and distribute it into the front of the natural log of 5. Now, because again, the goal is to get x by itself, I can divide by the natural log of 5 so that this entire binomial is by itself, and then subtract 1 from both sides so that I get x all the way by itself. Remember, we do not want to evaluate until we have x completely isolated, so don't start typing stuff into your calculator too early. You only want to type stuff in your calculator one time so you get a good approximation for x and you only round once. Let's have you guys try example C. This one's really similar to example A if you want to look back at one to have an example. Pause the video now because the answer is just going to appear. All right, so in this problem, although it's very similar to question A, we get to use a different property to be able to solve this. If you recognize that natural log of e is a logarithm with the same base for the log and the exponential, these are going to cancel each other out and just the exponent is left over. So the moment we take the natural log of both sides, we can cross out natural log of e, and we just have 3x equal to natural log of 8. Divide by 3 on both sides, and then plug into your calculator to compute. Natural log of 8 divided by 3 is approximately 0.693. Question D is very similar to A and C, so I'm not going to spend a ton of time going over it, but we can just take a quick second to look at it. We would isolate the exponential expression in 2 steps, first by adding 1 to both sides, and then by dividing by 3. Because remember, the exponential expression is just purely the thing with an exponent, not any coefficients in front of it. So we would actually have to divide by 3 to start working with the natural logs. We take the natural log of both sides. The natural log of e is going to cancel out using the identity property, and we're just left with 2x. But then we have 2x equal to the natural log of 13/3. So we're able to just divide by 2. So that x is isolated, and then we can compute all of this in our calculator so that we get x is approximately 0.733. Now this next problem, yes, I already did for you, but I'm going to spend some time going through it, and I actually am going to write down what happened each step so that you can also have good notes. Now if you notice, when we start this problem, I've already highlighted these blue because there is an exponential expression on both sides. It is as isolated as we can get it because it's isolated on the left and isolated on the right. It's okay when that happens. Just know that this question is going to be slightly more complicated. So we take the natural log of both sides. That step's the same once it's been isolated. We then notice that we have these powers here and here that can come up to the front of each natural logarithm. That's the power rule. Okay, so then I'm left with 2x plus 3 times the natural log of 4 equal to x times the natural log of 5. Remember, I'm trying to solve for x, so I want x's to all be on the left-hand side of the equal sign. So the first thing I'm going to do here, I drew with the little black arrows there is to distribute. I'm distributing the natural log of 4 because I need every x term by itself outside of a parentheses. Then in one fell swoop, what I did from this step to this step, okay, so to get from after the distribution to the next step, is I went ahead and moved all of the x terms to the left-hand side and all of the non-x terms to the right-hand side. By x terms, I mean the terms with an x in them. Obviously, this term, to get it to the other side, I would need to subtract it. And this term, since it doesn't have an x in it, to move it to the other side, I would also subtract it. Okay, so that's just moving all of the x's, so variables, to the left-hand side, and all the non-variables to the right-hand side, whatever sort of algebra it takes for you to do that. After this, I noticed that there are 2 x terms on the same side, which means this right-hand side have a number in common. They have a GCF. So I'm going to factor out the GCF, which is just factoring out the number x. Now x is in front. It's like I took both of them and I did reverse distribution and put it up here. Okay, so we divide out the GCF. And then if I notice, x is almost isolated except for right now it is being multiplied by this entire parentheses. So I'm going to divide by this entire parentheses as if it was just some number that I wanted to isolate from x. So we would have x is equal to -3 natural log of 4, all divided by the entire parentheses, 2 natural log of 4 minus natural log of 5. I can throw all of that into a calculator because it's just numbers at this point. There are no variables except for over here. And I get that x is approximately 3.576. Now, this example you're going to see a lot, and you're about to try one with me, but if there's a spot right here that you don't understand on example E, before we move on, raise your hand and ask a question. Okay, let's do example F together. It's going to be very similar, if not a little bit harder than example E. Okay, if we start from the top, we want to isolate the exponential expression. Well, both sides there are numbers with powers, and in the powers there are exponents. So it's as isolated as I can get it, which means I move on to the step where I take the natural log of both sides. So I'm going to do the natural log of 3 to the 2x plus 1 power equal to the natural log of 6 to the x plus 2 power. Since I have powers inside of my logarithm, I'm going to use that power rule to take the exponents and move them to the very front of their particular natural log. So the next step of this equation would say 2x plus 1 times the natural log of 3 equal to x plus 2 times the natural log of 6. Yes, the parentheses are important since you're multiplying a binomial times a single number. And yes, natural log of 3 is a single number. Now, hopefully your spidey senses are saying, we have numbers multiplied in front of or behind parentheses, which means I need to distribute on both sides. So my next step after distribution would say 2x times the natural log of 3 plus 1 times the natural log of 3 equal to x times the natural log of 6 plus 2 times the natural log of 6. All right, we've got a lot of terms going on. I see that there are two terms that have equal or x's in them, here and here. I want both of those terms on the left. I see these two terms do not have x's in them. I want those on the right. This is just basic solving. And I'll actually show these in between steps this time, just in case you need this example. I'm going to subtract x natural log of 6 from both sides. Now it doesn't combine with anything, so I'm just going to write it on the right hand side so that I know it's going over there. But I'm also going to do the opposite of natural log of 3 since I want that to cancel. And I'm going to subtract natural log of 3 over here. But it also does not combine with anything. There are no like terms. I mean, it's just a constant number that I don't know in my head, but it's not like we can combine those natural logs in any way. So we would have 2x natural log of 3 minus x natural log of 6 equal to 2 natural log of 6 minus natural log of 3. So all of the x terms are on the left-hand side, and all of the non-x terms are on the right-hand side. I'm going to factor out the GCF, which if you notice, both of these terms right here have an x in them. So I'm going to factor that x out into the front of that binomial. So this would be 2 natural log of 3 left over, and just natural log of 6 left over, equal to 2 natural log of 6 minus natural log of 3. To isolate the x, I would want to divide by its coefficient, which happens to be that parentheses with the natural logs inside of it. So I'm going to divide both sides by that entire binomial, which means this would be 2 natural log of 6 minus natural log of 3 in the numerator, all divided by that parentheses. 2 natural log of 3 minus natural log of 6. And at this point, I have x equals something, which means that's when I turn to my calculator to evaluate. This would give me approximately 6.129. Remember, we can always check our work by storing this answer or using second, I think it's the negative sign, second negative back in the original question to be able to see if these two things are actually equal to each other. If we typed exactly this in, 6.129, because we rounded it, it would not give us a true mathematical statement. So we want to store the exact answer each time. Again, if these two examples, E or F, some part of it does not make sense to you yet, please pause the video and ask me a good question. Now the last three examples are all similar. They're what's called quadratic form solving. Now quadratic form, it's because it's actually written like a quadratic. So if I were to write g instead of with an exponential, if I were just to write it as x squared minus 4x plus 3, this would be very easy to factor and solve. The reason I know that this is the same is because all I've done is substituted e for the x as x. Notice this says 4 e to the x. I made that x. And e to the x squared is e to the 2x. So that's just x squared. So this is really just a quadratic that instead of we're using x's, we're using e to the x's. And now we would guess and check this. We'd set it up for factoring. It would be x and x. We want factors of 3 that would add to negative 4. Well, the only things that multiply to 3 are 1 and 3. And to make that negative 4, I need to make them both negative, which is exactly how I got e to the x minus 1, e to the x minus 3. The exact same things I had if I had treated this like a quadratic. The key to knowing that you're going to use quadratic form is the fact that there are 3 terms and that one of the terms is a square. Now, once we have it in quadratic form, we actually create 2 tiny little exponential expressions or equations that we need to solve. So if you follow along with me, once we have it here, we use the zero product property like we always do to set these equal to 0, the factors. And then I quickly solve for e to the x. So I added 1, I'm just going to do this side first, by the way. I added 1 to both sides and I got e to the x equal 1. Well, that is an isolated exponential expression, just like we were doing in the previous examples. So I would take the natural log of both sides and apply the different properties. Here, natural log of e is going to cancel out, so I'm just left with x. X is equal to the natural log of 1. I compute in my brain or in my calculator for this one, and we get x that is exactly 0, because the natural log of 1 is 0. And then we do the same thing for the other factor. E to the x minus 1 equal to 0 is the same as e to the x equal to 3 because I added 3 to both sides. We take the natural log of both sides. The natural log of e is going to cancel because of the identity property. I'm left with x is equal to natural log of 3, which beam, put that in my calculator. I get that x is approximately 1.099. And that's quadratic form. So we treat it like a quadratic to factor it first. And then we finish solving it the way we have all of the other exponential equations. So let's try one together. So first things first, this one is not set equal to 0, so I couldn't have even solved it if it was a quadratic. So we first things first set it equal to 0. This would be e to the 2x plus 5e to the x plus 6 equal to 0. All right, great. I know that this is going to factor, hopefully, because it's in quadratic form. It looks like a quadratic because it's got something squared plus 5 times that something plus some number. So we set up our factors. This time, instead of with just x in the front, there's going to be e to the x's in the front. But the other rules for factoring still applies, which means I'm looking for numbers that multiply to 6 that would add to 5. The first thing I think of when I think of numbers that multiply to 6 is 1 times 6. But if I do this, at no point does 1 and 6, when they're both the same sign, make positive 5. One of them would have to be negative. So I'm like, back to the drawing board. The next numbers that multiply to 6 are 2 and 3. And they would both need to be positive. 2 plus 3 is 5. Great. So now that we have the whole expression set equal to 0, we're going to take each little expression, each factor, and set it equal to 0 due to the zero product property. I'm going to do this first one first. We need to isolate the e to the x. So it'd be e to the x equal to negative 2. I'm going to take the natural log of both sides. So natural log of e to the x equal to the natural log of negative 2. The natural log of e is going to cancel, so I'm just left with x equal to natural log of negative 2. Now, if you throw this into your calculator is going to tell you non-real answer. Remember, natural logarithms or logarithms, their argument must be greater than 0. So like this doesn't work. This would be a no solution from this one. So we throw that answer away. We go to the next one. We're going to subtract 3 from both sides, and then we're going to take the natural log of both sides. Natural log of e to the x equal to the natural log of negative 3. Hopefully you're starting to notice it. The natural log of e is going to cancel. We'd have x equal to the natural log of -3. But again, if you threw that into your calculator without thinking, your calculator would tell you non-real answer. Because again, the argument, the parentheses of any logarithm, natural log or common logarithm, cannot be negative. So we have to throw this answer choice away. When you throw both of them away, the only thing you would say is no real solution. So this particular one, because we threw away both of the answer choices there, we'd say no solution. One more example before we start solving logarithms is this example here. Now, I'm not going to make you do this one on your own because it's another quadratic form, and it's an even funnier looking quadratic form. Because if you notice, this is still something squared. If these were just x squared, this would be x squared minus 6x minus 7. But instead of x's, looking at that middle term, I've actually got e to the 2x's. So that's what I'm going to start my parentheses with. So my parentheses, when I'm factoring this, would be e to the 2x and e to the 2x. But now we treat it just like it was a regular quadratic. We want factors of -7 that will add to -6. Well, the only numbers that add to 7 are 1 and 7, so I'm going to put them here. And to make -6, I would need a big -7 and a small +1. Once it's factored, we take each factor itself and set it equal to 0 so that we can solve. I'll do this first one first. To isolate the exponential expression, we're going to subtract 1 from both sides, and then take the natural log of both sides. Hopefully you're starting to notice again, when these cancel out, you're left with 2x equal to the natural log of -1. Just to keep going, this would be x equal to the natural log of -1 divided by 2. But if you threw that in a calculator, it would tell you non-real answer, because again, we can't have a negative number being what we're computing inside of a natural log. That's the argument. So this side, we're just going to cross out. But we got to check the other side. So we isolate the e to the 2x term, the exponential expression, by adding 7 to both sides. We're going to take the natural log of both sides. The natural log of e is going to cancel. This will be 2x equal to the natural log of 7. That's not negative, so I'm good to keep going here. We divide by 2 on both sides to get natural log of 7 divided by 2. And if we throw that into a calculator, since it's not going to tell me non-real answer, I have got a positive number inside that logarithm. It's going to be x is approximately equal to 0.973. So this one only has one solution, which is fine. It only has one time that it's going to cross the x-axis. So there's tons of different types of exponential expressions or equations you might be solving, from something simple like answer or question A to something a little bit more complex like E to something that even looks like a quadratic like that whole last row. If you're confused on any part of any example, pause the video and call me over, please. Because now we're going to be working on solving logarithmic equations, so the opposite type of equation. The steps for this is that we are going to condense to a single logarithm using the different properties that we talked about last class. Then we're going to use that log loop to get rid of the logarithm itself. We should end up with some sort of exponential equation, or even more simply, a sort of linear equation. We solve for x, but then we have to remember to check for extraneous solutions. So we're going to look at restrictions at the beginning of each of these problems. Because remember, and we just talked about this, that the argument or the parentheses of any logarithm has to be greater than 0. So we're going to be looking at all these restrictions each time we do this. Okay. Now, letter A here, super simple. It does not have anything I need to condense because I only see LOG. I only see one logarithm. LOG is only written once. So I go ahead and do the log loop, which means I keep the base the same, the base here is 4, and I'm going to loop the other two things. Log, loop. Fabulous. This is going to be 4 to the second power equal to x plus 3. That's the log loop that we worked out with properties. Well, if you look at what's left here, and if I just do a little bit of math, well, 4 squared is 16. And then to solve for x after that, I just have to subtract 3 from both sides. So x is equal to 13. Now we needed to make sure that this abides by any of the restrictions that we set at the beginning of the problem. So if I look at the restrictions, I know that x plus 3 has to be greater than 0, which means solving for x, that x has to be greater than negative 3. Well, is 13 greater than negative 3? Yeah, obviously. So it checks out. There's no extraneous solutions here. So as these problems get more complicated, we're going to want to check these restrictions first, because in the next couple problems, there's going to be more than one thing that will be inside of a logarithm, and we want to start with the original restrictions. So if we go to B, notice I see the word log, I see logarithm written twice. So we're going to have to do some condensing so that it only has one. But before we start condensing, let's check our restrictions. That first logarithm has an argument of x, and we know that then x has to be greater than 0. So if we get a negative number, we're going to throw it away. We also know that x minus 7 has to be greater than 0, which means x is greater than 7. So if we get any number that is less than 7, we also throw it away because it has to work for both logarithms. So really, we're going to want to pay attention to this restriction, since things that are bigger than 7 are bigger than 0. It's our most restrictive restriction. But okay, let's start condensing. Now, we had a rule last time that if we were adding logarithms, that we would multiply their contents. So this should really be the logarithm log base 2 of x times x minus 7, close parentheses, equal to 3. Now, I'm going to do an extra step here. You probably could do this part in your head, but I'm going to go ahead and show what that looks like whenever we were to distribute this out, just because that will make the next step easier. All right, so I've multiplied them. Now I'm going to use the log loop. Remember, the log loop keeps the base the same, takes the number from the opposite side, and sets it equal to the stuff inside the logarithm. That's the log loop. So this goes here, and this goes here. Okay, cool. Now if we look, last time we had a linear equation, but if I multiply 2 to the thirds out, please do not write down 6. Oh my goodness. This is 8. So we have 8 equal to x squared minus 7x. And if I put all those numbers on the same side, you should hopefully notice that this is a quadratic. And we know how to solve quadratics. We do that by factoring and solving each little factor. So we would set up and solve a factoring problem. The things that multiply to 8 and that add to negative 7 are negative 8 and positive 1, which means that we would solve both x minus 8 equal to 0 and x plus 1 equal to 0. Well, this will give me x equal to 8, and this will give me x equal to negative 1. One of those solutions is extraneous. Which one is it? Yeah, remember that we said at the beginning that the number had to be bigger than 0 and bigger than 7. So negative 1 is out. It's not bigger than 0, nor is it bigger than 7. So x equal to 8 is the only solution here, and it fits both of my restrictions. So solving logarithms, if you can remember how to condense them, are extremely easier because we're not dealing with as much computing in the calculator that we can't do in our head. Now let's look at this next one that I've annotated for you, question C. So in the first step that I've shown so far, all I have done is move this natural log that was on the opposite side of the equal sign to the same side as the other natural logs, because now it's subtracted. I also used the property of addition to do this multiplication. So condensed those two logarithms together using multiplication. But of course, because I moved that other natural log over, it is now being subtracted, which means to continue to condense it, I would need to divide by this argument. Okay, now I distributed this x up here in the numerator because I wanted to be able to condense it further. But once I have it condensed into one logarithm, I use the log loop. Now remember, the base of any natural log is the number e. And then I log looped it. E to the 0 equal to the argument. Now, e to the 0 is something I can do in my head. Anything to the 0 power is 1, so it's like I have 1 equal to this entire left-hand side. Now, what I did from here to here is I just multiplied both sides by the denominator. So I multiplied this side by 2x plus 7 because it's going to cancel this out. And I multiplied this side by 2x plus 7. But 1 times 2x plus 7 is just 2x plus 7, which is what I have written down next. Now I moved these terms back to the left-hand side using subtraction so that I got 4x squared plus 27x minus 7. And I recognize this as a quadratic. So I guessed and I checked my factoring and set both terms equal to 0, both factors equal to 0, and solved. Now if I look back at my question, the very beginning says that x has to be greater than 0. That comes from this restriction. Then I set this part greater than 0. And I got x is greater than negative 29/4, which that's negative 7.25, which might be easier for us to look at later. And then the last argument, 2x plus 7, I also said has to be greater than 0. So x has to be greater than negative 7/2, which is negative 3.5. When I solved these, I got x is equal to 1/4 and x is equal to negative 7. But negative 7 is not greater than 0 or even greater than negative 7.5. So I had to throw this one out. It didn't work for every restriction. So I only had one solution. Now I want you to try D here. I'm going to just have the answer appear in a second. So go ahead and pause the video now and try this problem on your own. On this problem, we would condense the logarithms and then use the log loop so that we have 8 equal to x plus 2 divided by x minus 5. We'd multiply both sides by x minus 5, essentially moving it back to the right-hand side, and distribute the 8. Then we subtract the numbers to get them to combine like terms on one, either side, doesn't matter, of the equal sign so that it said equal to 0. We notice this is now a linear equation, so we're able to solve for x without factoring, and we get x equal to 6. But I have to make sure that this fits my restrictions. X plus 2 greater than 0 means that x has to be greater than negative 2. Check, it is. And x minus 5 greater than 0 means that x has to be greater than 5. And yes, 6 is greater than 5, so this checks out. And it abides by my restrictions. That's where we're going to stop today. We just want to be able to solve exponential equations and logarithmic equations. Next class, we're going to work on some real-world applications of these, which continues us in the solving of these different types of equations.